So in this lesson, we are going to look at infinite geometric series. But for those who are missing last day, we'll actually start it off with a quick review of finite geometric series. And you guys hopefully remember that a geometric sequence is a list of numbers, and you get each term by multiplying the term before it by the same number each time. So in our example, right here, we multiply each term by a half to get the next term. In general, for geometric sequences, if you start off with term 1, you multiply that term by the common ratio, r, to get the next term. Then multiply that by the common ratio again to get term 3. Multiply it by r again to get term 4, etc. Giving us the general term of t1 times r to the n minus 1. So let's apply that to question A. They want t9. And remember here, we have r equal to, or t1 equal to 1, and r is equal to a half. So this is our formula for the general term, and we want t9. It's 1 over 2 to the 8. Okay, 1 over 2 to the 8. 8 is 256. So it's 1 over 256. Great. So then the next question is calculate S6. Now we actually proved in class last day the formula for S6. And that formula, in general, for a geometric series, you're adding up the first n terms. The formula is t1 times 1 minus r to the n divided by 1 minus r. If you missed last class and you'd like to see a proof of this formula, just ask me next time I'm there. So in S6, 1 times 1 minus 1 half to the 6 all over 1 minus 1 half. Let's simplify that a little bit. So this is 1 minus 1 half to the 6 is 1 over 64 over a half, which is 63 over 64 times 2. If you flip the 1 half to make it multiply by 2, which is 63 over 32. So that's S6, 63 over 32. It's a number. It's a little bit less than 2. And basically, the two formulas for geometric sequences and series we've covered so far that you have to know are exactly these two formulas. So now we're going to look at a really interesting case. So let's look at this exact same sequence. 1 times a half times a quarter times an eighth. And we want to say, okay, well, what happens to Sn as n gets really large? So in the previous example, we looked at S6, and we're going to look at Sn for really large values of n. And so in other words, we're looking at what happens to this formula. So it's t1 times 1 minus r to the n over 1 minus r as n gets really big. Or if you remember our limits, as n goes to infinity. But if you don't remember limits, that's okay. So in our particular case, Sn is 1 times 1 minus 1 half to the n divided by 1 minus 1 half, or 1 minus 1 half to the n over 1 half. And if you still really want to simplify it more, in this particular case, it's 2 times 1 minus 1 half to the n. At these Sn's as n gets really big is to actually let the computer do the work for you. So I've created an Excel spreadsheet here that you can see. And you can see in this column, this column, we have all the values of n. So n is 1, n is 2, n is 3, n is 4, etc. In column C, I have what Sn is for that value of n for our particular sequence. So, the first is 1. If you just add the first term to itself, 1.5, 1.75, and we're interested, what happens as it gets really big? Well, as you can see at about term 22, it tells us it's equal to 2. Now that's not entirely true. What's actually true is that it is so close to 2 that the computer thinks it's 2. In other words, as the sequence gets huge, we get really, really, really close to 2 for our value. And in fact, we're never going to go over 2. So in a sense, if I added all infinity terms of this sequence, which we call S infinity, that is equal, in this case, to 2. Really what's true is that the limit of this, as n goes to infinity, is equal to 2. Now, let's look at this formula again. What happens when n gets huge? Well, when n gets huge, r to the power n, in our case, where r is small, so here's if r is less than 1 in absolute value, then S infinity looks like t1. This r to the n goes away for S infinity because this number less than 1 to the power n is very small, over 1 minus r. All infinity terms, you add them up, this formula will give you what you would get. And that's kind of amazing. And note quickly that this only actually works if your common ratio is less than 1. Let's look at this series where you multiply by 3 every time. Okay, let's look at this series. So here, the r value is 3, and t1 is equal to 2. Now, if I add up every term, if I add up all the terms, 2 plus 6 plus 18 plus 54, all infinity of them, that is never going to give you a finite number because each term is bigger than the last. But in the sequence we just looked at, each term gets small. As n gets big, they're insignificant. And so really you just get closer and closer to 2. That's your upper limit. So let's do one example. So let's look at this geometric sequence. Here, t1 is equal to 100, and the r value is a quarter. We're dividing by 4 every time. Okay, it says calculate S infinity. Well, let's use our new formula. 100 over 1 minus a quarter, which is really 100 divided by 3/4, which is equal to 4 times 100, 3, which is 400 over 3. Now, what does that mean? If you took Sn, the formula, and you put it into your calculator, and for n you put something really big, like 1,000, it would be extremely, extremely close to 400 over 3. And the bigger you put n, the closer it would be to 400 over 3. And remember, this works because r is less than 1. So it will not work otherwise. So that's really all you have to know for infinite geometric series, that if r is less than 1, this formula applies. And it's kind of amazing that you can add an infinite number of terms and get a finite result. So give the questions I've left a try. And then this is really the end of the sequences and series unit. So make sure you know it well. Thanks.